All right, problem number 2, G period. We tried to do this problem together, and I'm so sorry it worked out the way it did, where I think I had a couple of numbers off. So I have a fresh version here, and you should trust the version on the video. So we want the period of the mass, and this is kind of a trick question because I have the word mass here, and I'm asking for the period. And your brain may want to use T equals 2 pi square root of m over k. Not recommended. This is still a pendulum problem. So the period is going to actually be T equals 2 pi square root of L over G. And so when we actually plug in our numbers, it's going to be 2 pi square root of, and this is going to be 3 meters over 10. When we actually throw that into our calculator, we will end up getting 3.4 meters. And then the mass is released from equilibrium. We want to know its speed at the bottom of the swing. This is actually a conservation of energy problem, so let's be careful. We have all gravitational energy here, and that gets converted into kinetic energy at the bottom. So we'll have Eg equals Ek. That's mgh equals 1/2 mv squared. The m's cancel, and we end up getting 2. Whoa, got a word there. Whoops. So we'll end up getting here, the m's cancel. Let's actually plug in our numbers to get v, and when we do that, we're going to end up getting 2 times g times h equals v squared. And so v is going to equal the square root of 2 times 10 times 0.6. And when we actually work that out, that ends up being about like 3.5 meters per second. All right, now when we want to get the tension in the rope at the bottom of the swing, the way that's going to work is we're going to have the tension, the weight pointing down, because we're at the bottom of the swing. So we have T minus W, and the effect of that is that we get mv squared divided by r. I've skipped a step here. I should be really clear. This is the acceleration going in a circle. This formula is not given on a formula sheet. You need to be able to go from this free body diagram to this equation here. So the idea is that we're not in equilibrium at the bottom. So we have tension minus 0.2 times 10, that's mg, equals 0.2 times, now let's see, v squared, that's 3.5 squared, which I'm going to go up to the square root here. This is actually the square root of 12. I'm going to work that math out. So this will be 0.2 times 12 divided by my radius, which is going to be 3. So that's t minus 2 equals 0.2 times 4, which is 0.8. So the tension is 2.8. So if we can support 15 newtons of tension, but we have 2.8 newtons of tension, we don't break, because 2.8 is less than 15 newtons. So we're good on that. So that is the second page of the practice test.